So welcome to this talk. I will present my paper entitled Self-Powered CMOS Active Rectifier Suitable for Low Voltage Mechanical Energy Harvesters. I will start with the motivation and the state of the art. Then I will present the design of the self-powered full-wave active rectifier. Then I will show the simulation of the experimental results of the proposed system. And finally, I will conclude my talk. Microscale energy harvesters, including electrostatic, electromagnetic, and piezoelectric systems, typically produce output voltages in the range of some hundreds millivolts up to 1 or 2 volts and low output power. This amount of low power introduces the challenge to design efficient power management systems suitable, which are converting alternating signals produced by these harvesters to DC form. Typical energy harvesting system consists of the energy harvester, an AC to DC converter, a maximum power point tracking circuit, and a power storage unit. The AC to DC converter is a crucial component in the power management system of the energy harvester, which should convert AC to DC signals with the possible minimum amount of power to increase the power efficiency of the energy harvester. Passive and active rectifiers have been used to convert alternating signals produced by these harvesters to DC signals. The full-wave bridge rectifier utilizes 4 diode connected transistors as one of the widely used circuits. A significant amount of power is dissipated in this circuit due to the high threshold voltage of the diode connected transistors. The gate-cross coupled rectifier is an improved version of the bridge rectifier circuit, where two diode connected transistors are replaced by 2 NMOS gate-cross connected transistors, and so the voltage drop is reduced to 1 threshold voltage plus the drain source voltage of the NMOS transistor. In the bootstrap configuration, the 2 diode connected transistors are replaced by the bootstrap diode, which is formed by 3 PMOS transistors and 1 capacitor as shown on the right here. So the total voltage drop is the drain source voltage of this transistor plus the difference of the 2 threshold voltages of the transistors MB3 and MB2. In the active configurations, diodes are replaced by comparator controlled transistors. In this way, the threshold voltage is reduced to few millivolts. The synchronous rectifier is one of these examples where 2 comparator controlled transistors are used to control the current flow in the output direction. Another version shown on the right combines the negative voltage converter with an active diode to prevent the current flow from the output to the input. In this work, I will introduce a self-powered full-wave active rectifier suitable for low-voltage energy harvesters. The proposed system consists of 2 stages, the negative voltage converter stage and an active diode. The negative voltage converter stage converts negative half cycles of the input waveform to positive ones, and the active diode is implemented as a comparator control PMOS switch that controls the current flow in the output direction. So when the output of the NVC circuit, VNVC, becomes greater than the DC output, the comparator signal controls the switch, and the switch turns on, allowing the current to flow in the output direction. The comparator has been designed in the sub-threshold region to minimize the power consumption of the circuit to the nanowatt range, and it is powered from the output of the rectifier. Also, a passive path is included between the output of the negative voltage converter stage and the output of the rectifier to charge the circuit at the startup to supply the comparator. A high-performance nonlinear comparator is used to build the active diode. It consists of 3 stages: the preamplifier, the decision circuit, and the output buffer. The preamplifier is a differential amplifier with current mirror loads and both NMOS and PMOS transistors at the input of this stage to have input common mode range beyond the supply rails of the comparator. The preamplifier is responsible for increasing the comparator sensitivity, and it also amplifies the signal. The second stage is the decision circuit, shown here, and it determines which input is larger depending on the two output currents, IOP and IOM. It also uses the positive feedback connection from the transistors N9 and N10 to increase the comparator gain. The system has been built in cadence spectra and simulated also in cadence. This figure shows the transient response of the proposed system at the steady state. The dashed line is the input of the rectifier, and the solid blue line is the output of the negative voltage converter stage. In the zoom, as shown in the zoom figure, when the output of the negative voltage converter stage becomes greater than the DC output, the comparator signal goes low, allowing the current to flow in the output direction. The result of this simulation is the output DC is 860 millivolts with 35 millivolt ripple voltage, providing an output current of 17 microamperes for a load of 50 kilo ohms and 1 microfarad smoothing capacitor, and the simulated power efficiency is 96%. The chip has been fabricated in 350 nanometer low threshold CMOS process from X-FAB. The die photo is shown on the right. The active area of the die is covered by dummy devices from X-FAB. That's why the layout of the chip is shown on the left. And these three stages, the switch stage, the NVC stage, and the comparator, are highlighted in this figure. The chip area is 470 by 500 square micrometers, and the active area of the chip is 200 by 320 square micrometers. The power efficiency as a function of the output load at different peak input voltages is shown in this figure. The power efficiency is calculated by measuring the output power and the input power according to this equation. As shown in the figure, the system is able to rectify signals with a power efficiency over 90% for a wide load range, for a load range of between 20 and 175 kilo ohms for inputs over 750 millivolts. It should be mentioned here that the power consumption of the active components is taken into account in the power efficiency calculations. Also, as you can see, the power efficiency decrease when the output load becomes greater or smaller than specific value due to the impedance matching between the output of the rectifier and the output of the rectifier and the rectifier itself. The power efficiency as a function of the peak input voltage at two different loads is shown in this figure. The maximum measured power efficiency is 96% at an input peak voltage of 900 millivolts, providing a current of 17 microamperes. The working range of the proposed rectifier is between half a volt and 1.5 volts. It can be seen that the system transitions from the passive to the active mode between 400 millivolts and 500 millivolts. That's why you can see this dip in the efficiency. Also, the voltage efficiency as a function of the load is at different peak input voltages is shown in this figure. The voltage efficiency is calculated by measuring the output DC and the input peak voltage according to this equation. It can be seen that the system is able to rectify signals with a voltage efficiency over 90% for a load range greater than 30 kilo ohms and inputs over 750 millivolts. So the results of the fabricated chip is compared to the state of the art in this table. So it can be seen that the chip provides a competitive set of specifications compared to other published work. For example, the power consumption of the comparator is reduced to 45 nanowatts due to the architecture used, which is the positive feedback in the decision circuit. Of course, the 45 nanowatts is at 500 millivolts. It goes up to 250 nanowatts at 900 millivolts. Using this comparator architecture, the power efficiency, the maximum measured power efficiency is 96%, which shows an improvement over other published work. Also, the working range of the system is between 0.5 and 1.5 volts. These calculations and measurements are done with a frequency below 6 kilohertz, and the voltage efficiency goes up to 98%. As a conclusion, I have presented a self-powered full-wave active rectifier consists of two stages, the negative voltage converter stage and the active diode. A high-performance nonlinear comparator is used to build the active diode. It is working in the sub-threshold region to reduce the power consumption of the circuit, and the maximum measured power efficiency is 96%. The outlook is to put this rectifier in the chain of the energy harvester and measure the output the power efficiency with a real harvester, and maybe also integrate DC to DC converter to have the impedance matching of this rectifier to increase the efficiency. Of course, for the loads below that specific value that we have shown. Thank you for your attention, and I appreciate your questions.